So, what's up, guys? I wanted to basically this week. I wanted to like when I was making this presentation, I just wanted to throw out like a couple questions that I was thinking about as I went along this, and yeah, hopefully that'll like answer some of them. So the first thing that I learned and I wanted to answer was, why does sound trail off? So like whether you're speaking to someone face to face or whether you hear a train from, let's say you're in your dorm room, right? And you always heard that train at 2 a.m, like, why do you still hear that, but why is it quieter? So the reason is sound has a characteristic to it called attenuation. And basically what that is um, you can think of, like we talked about frequency. Um, you can see this as a sine wave, but it's over time and over distance. It's actually slowly decreasing. So this is like, you can think of this as volume, the y-axis, and it's just slowly getting quieter and quieter. And the reason why it gets quieter over distance is because of friction in the air. So sound is made up of waves, like pressure in the air, and air has an associated friction to it, and that's what this equation actually shows here. So it wouldn't be an AEE presentation without some Desmos, right? So I wanted to show, I'll get out of there, don't show me. I wanted to show what's going on here. So what this equation was it was called a Stokes law of attenuation. So you have your starting amplitude. So basically wherever the sound occurred, so you can think of that as your A0, like right at distance 0. That's going to be like the amplitude of, or like that's going to be the volume of the sound, right? So I just have it at 2 here. And this is the equation. So if I were to show, let's go to 1 to show this. So if I were to start off at 1, and we just had a regular old sine wave, right? And this is over distance. Without that attenuation, that's what this would look like. So without the volume going lower and lower, like if there was no attenuation, the train that is right by Trowbridge, if we were in our dorms and we didn't have this attenuation, we'd hear it basically. If we were, it would be like standing right next to the train. That's how loud it would be. But what ends up happening is actually this, right? So this is the x-axis is distance. So you can see that it slowly rolls off as you go farther and farther. So to show the train, let's increase this like really loud, right? This is why you can hear the train, like the train's a lot quieter, like as distance is farther, but like when you're more up to it, it's like super loud. And then if you're just like talking in a normal voice, you can still hear it. And by the way, this guy right here is the attenuation constant, and this is determined if you go back to the equation. This is determined by what medium you're in. So in this case, we're in air. So I did the this is density of air. This is the velocity, so speed of sound. This is your angular frequency. Frequency dependent, but it's not going to matter that much because this eta here, I forgot what eta was, but it's a very small number. So yeah, that's why sound gets quieter and quieter as you get farther and farther away. So there's a video I found on it that this guy gives a pretty good like visual example.
It's almost a free field. We have some reflection off the ground, but we have that wall over there. And that wall is reflecting the sound of my voice. So the sound goes out, it hits the microphone at 1 meter away. It also goes in that direction, bounces off the wall, and comes back. You probably can't hear that reflection right now. You can't hear it as a separate echo because it's so quiet. And it's quiet for two reasons. One is that there's attenuation or reduction in the level caused by the distance to the wall and back. The other is that the sound of my voice in that direction is quieter than it is in this direction because of the directional characteristics of my voice. But if I were to make a sound that is omnidirectional, so it radiates in all directions, and it's very short, then you'll hear the direct sound and the reflection as two separate things. So you can hear that echo coming in after the direct sound.
Yeah. I don't know if you guys could hear that clap, but if you actually pull up this YouTube video, and I have it linked at the bottom, but you can hear it. You can hear it like separately, and it's a lot quieter. So hopefully you guys can hear that. Okay, so the next question that I wanted to answer was, how do we characterize how loud sound is, right? So we were talking about uh, why the train sounds quieter when we're in our dorm. We can still hear it. So we like to use the term decibels. So instead of so like this, instead of characterizing it by like amplitude, like how intense the sound pressure or how intense the pressure of the wave is, we'd rather use decibels because it's a lot easier uh, to describe the sound. So the way you can um, the way you can figure out how many decibels a sound is by these equations down here. Um, and I'll show a video here in a second, but basically, uh, if you don't want to look at these equations and do it, I totally understand. So like basically you take like the distance of how far you hear a sound, and um, every uh, every time you go twice the distance of that sound, it's going to be 6 dB quieter. So that's what you would say. Like if you were trying to characterize the sound, it'd be 6 dB quieter, or if you were 2 times closer, it'd be 6 dB higher. So yeah, that's what this guy shows here.
Is the level of my voice. I'll keep talking at hopefully the same level, and I'll half the distance. I'll go from 1 meter to 50 centimeters to the camera and the microphone, and then I'll go back again to the 1 meter mark. When I half that distance, so if I come back to 50 centimeters, I half the distance. That means I get 2 times the level of my voice. That's equivalent of a 6 decibel increase. So here I'm 6 dB louder than I am right here at the 1 meter mark. If I then double my distance and go back to 2 meters away from the microphone and the camera, now I've dropped by half and therefore a 6 dB reduction in the level of my voice without having changed anything. I'm still trying to talk at the same level, and I haven't changed the level of the fader in the software, for example. If I go back to 4 meters, so now I've doubled that distance again, that's another half. So this is 1/4 of the 1 meter distance level.
So yeah, kind of shows there the decibel thing. So like I said, so the reason why it's so nice to use decibels is it's a pretty easy way um, to like characterize how loud different sounds are. So I found this from Purdue Purdue actually measured a bunch of different sounds, like how loud they are, and it starts to like very quiet sounds like breathing and whispering to extremely loud sounds like you know a plane getting ready to get off the runway. And I thought this was pretty cool because I actually didn't know like which sounds can actually damage your ears. Um, I was curious because I always listen to music like pretty loud. I listen to metal a lot and I blare it. So I wanted to figure out like, okay, what's my limit? And it turns out that there's actually it's not just how loud you're listening to it, it's also how long you're listening to the um like to that decibel rating. So like for instance, if you see people wearing like the earmuffs for when they're mowing their lawn, um that's there's actually something to that because if you're mowing your lawn for 8 hours, which no one does, but you could actually damage your ears because it's like it's at this level. So
So you're telling me 7 hours is okay?
you've listened to metal for 7 hours and you're fine.
Yeah.
There you go. I mean,
Does it work like that though?
I mean, I don't think
There
I've
has
listened to
to be
metal for
some
that.
sort of like damage,
What's
right?
that?
There has to be some sort of damage, like if you do for like 7 and not 8 or something, right?
Probably. I mean, I think this is an estimate, but
Okay.
yeah, I don't think this is like completely exact. But I mean, there's a reason though, like why a lot of musicians, like especially like Ozzy Osbourne, like he's completely just his ears are just messed up. So that's part of it.
I think he has more reasons to why he's messed up.
A lot more. I'm talking about ears specifically. Yeah, that's what this was. So yeah. Okay, so what people were probably interested in for acoustics is what does sound. So whether you're talking, whether you're listening to music, whatever you're doing, what does sound do inside a room of four walls, a ceiling, and a floor, right? So there's one of three things that could happen, if not all three happening all at once for a sound. So the wall um, can actually absorb the sound. So what that means is the sound wave that hits um, the wall would basically like take in the energy of that sound and it would transfer it into heat. Now it's a very like very small amount of energy, small amount of heat. So that's why you know, if you talk to your wall and you feel it, like you're not going to really feel any difference. Not that I've tried it. If I'm wrong, please correct me. But that's what's happening though. It's transferring it into another energy form. It can also transmit, which simply just means the sound goes through the wall. So I'll talk about why we hear bass. We always hear bass through walls and cars and stuff, but that's one thing sound can do. It can just go right through the wall, and then it can simply reflect. So it can just like a ball. If you throw it against the wall, it can just bounce right back at you, and that sound can do the same exact thing. And I think, yeah, I have a video for this. This guy explains it really well.
Seem complicated, so let's make it simpler. Most rooms have flat walls and flat ceilings, and sound bounces off of these. So how does that affect the sound? I'll use these two Nerf guns to demonstrate. I've got this one aimed so this disc goes directly to the ear. That represents direct sound. I've got this one aimed so that disc bounces off the wall and it represents reflected sound. I'll shoot them both at the same time. Reflected sound arrives at our ears later than direct sound, even though it started out at the same time, because it's traveling farther. And this wall is only one flat surface. There are at least 6 in the average room, and that's a lot of reflected sound. But why is reflected sound bad? I'll demonstrate using these two identical patterns. The blue pattern represents direct sound waves, and the red pattern represents reflected sound waves. They start out together, but when I move the red one backwards, like a delayed sound reflection, it creates destructive interference patterns which changes the original sound wave. Here's the problem. Original sound waves are distorted by strong, later arriving reflections. Also, sound travels really fast, about 1130 feet per second. A sound wave will bounce back and forth between these two walls about 60 times in 1 second. Sound travels so fast, it fills a room almost instantly, and this is only one bounce angle. Every room has thousands. How can we make our rooms sound better?
Okay, I'm going to get to that. So yeah, little video there explaining it. So I'm going to answer this guy's question that he just asked. How can we make it sound better? Basically, so to make this a more technical question, how can we prevent reflection and transmission from occurring, right? So bouncing back off the walls or going through the walls. So there are these things called sound absorbers and diffusers. And if you've ever gone into a recording studio or seen a recording studio, you've seen not to this degree, but foam pieces like this. And basically what they do is they take in the sound. Like I said, that's what absorption does. And what diffusers do, and I'll show it in the video in a little bit, but basically, if you don't want to just take in the sound completely, basically it takes the sound and it redirects it into several different directions. So it's one sound, but different directions. If you want it to sound more, if you want the room to sound, I guess, more full. And yeah, and a combination of these is, if you put this in a small room and you put all these absorbers and diffusers together, and I think this is actually a combination of both, but it makes it sound really, really good, specifically for vocals. So this guy is going to he's going to give some demonstrations of what I just said, basically.
Remember our Nerf guns? I'll shoot these at the same time, again representing a sound wave bouncing off a wall. Both discs bounce together in the same direction, which means the reflected sound is at full strength. Now let's use the first of our two acoustical tools, an absorber, to reduce the strength of sound bounces. To a sound wave, an absorber looks a little like a hole in the wall, so some of the energy doesn't come back. An absorber works by reducing the strength of reflected sound that would otherwise cause more destructive interference. But if we use only absorbers in a room, it makes it sound dull and unnatural. Historically, humans don't like overly absorbent rooms. So, let's use the second of our two acoustical tools, the curved surface diffuser. It also reduces the strength of sound bounces. A diffuser works by scattering the sound reflections in different directions, smoothing out destructive interferences throughout the room. Room acoustics are greatly improved using a combination of absorption and diffusion.
So like right there, you can hear that without them, it goes all over the place. But then with some of these diffusers and absorbers, it doesn't completely deaden, but it just makes it fuller. So yeah, and a lot of stuff in your room, like your bed and like your bed already acts as an absorber. So that's why your room doesn't, depending on what room you're in, you already have stuff in there that already is doing this. So I'm gonna get back to this later. I like I said at the beginning, I just learned about this, so I'll get back to what bass traps are. But this was another question I kind of came across, was why do we hear bass from like really loud parties and cars? So you like when you roll up to the stoplight, the car right next to you is just like vibrating your car with just loud bass, right? The reason we talked about frequency, um, we talked about frequency earlier. Frequency has an associated wavelength with it, and what wavelength is for the period that is associated with that frequency. All the wavelength is the distance between the period, like the start of the period and the end of the period. And the way you calculate the wavelength is actually this equation here, and the velocity is the speed of sound. You'll if you've taken any like radio frequency classes or anything with like with anything other than sound when it comes to frequency, this might be a little confusing to you. You might think, oh, like this should be c, right? Well, c is the speed of light. Here we're talking about the speed of sound, so this is actually going to be a different velocity. If this were the speed of sound, this wavelength would be ginormous. It would be miles long. So that's, just keep in mind that we're talking about the speed of sound. So with that being in mind, bass frequencies are, since they're really low, they're going to have larger wavelengths because you can see that from this equation. And a cool thing about, or like the reason why, like since their wavelengths are longer, they are actually able to travel through objects like walls and car windows and like the car body frame. And that's why you hear the bass when you're out, like when you're outside of a building and you hear the bass, that comes through the walls, not the higher frequencies. But as you enter the room, you obviously hear all the higher frequencies along with the bass because they're bouncing off the walls, but they're not going through the wall. So this kind of shows like a lower bass signal to like a mid-range signal here. You can see like this is a lot bigger than the higher frequency. Another thing too, we talked about resonance the other day. I learned that the reason why the car feels like it's shaking when you have, like if you listen to rap really loud in your car and some notes like don't really shake your car as others do, that's because of resonance. So the resonance is actually creating like literally a mechanical vibration on your car, like the side of your car. So it can also do that with walls. So there's a resonant frequency associated with every medium, like I said, in the resonance or in the frequency side / resonance presentation. So that's why there's like that's why there's a mechanical vibration to it. Okay, so I think that's it. So I wanted to go back to this bass trap. Basically, all I learned about it was that I guess another question is like, so how do you get rid of that bass, right? If you don't want to hear the bass like through the wall, if you don't want the bass signal to transmit, how do you prevent it? And I think this is the answer, is what is a bass trap. And basically what it does is it reduces the resonance in the room. So it reduces the, that little that mechanical vibration in your wall or your car door. So specifically for a wall, you would put this bass trap. It has to be at least 4 inches thick. The reason why it has to be so thick is because of the wavelength. Remember that. And yeah, that's the reason why it's placed in the corner. Is I think I saw something about the sound pressure is like the highest at corners in the room, so that's why I think it's also in the corner. Now, what I don't know of, and I'm going to look more into, is why there's a space behind here. But I did read up that there is supposed to be that triangular space there. Maybe it acts as like maybe this acts as a diffuser on the back portion of it. So maybe like the pressure point kind of hits the corner here and it's like trapped. Maybe that's what it is. Maybe it's literally trapping in the back of here. But yeah, this is a cool way. This is a cool way to reduce bass in a room. That's really all that's all I had today. So yeah, thanks.